the way I thought of going through today is to address some topics. I'm sure a lot of people have heard about HPC. What is the difference between HPC and grid? What is a data cluster? How do these things all fit together? The operation or the operating system and the management systems, how does that all fit together? GPU clusters, or can you actually use GPU clusters, or how do they fit together? The concept of bursting to cloud and my personal view of how you do that or what not to do. And then just some possible high-level thinking of the Matlab side of things and how that fits into the cluster environments. So it's going to be just a purely talk and chalk, and so just raise your hand or throw stuff if I'm not paying attention, and we can take it from there. So a thought to start, we're going to just draw. Let's just put that out of the way. Draw the architecture of what a cluster really is. So cluster has got a few basic components, and it sounds really simple, but when we start getting into the various details, it gets a bit more complicated. So the first thing, is you've got compute nodes. So we call them compute nodes. I'm going to draw a few of these. Oops. So those are the guys that actually do the real legwork of things. What we have on top of that, or separate to that, is actually the data. I'm going to call it cluster. And what we'll see when we go through all these various topics is that this is actually what makes your decisions. How you work with data, what you need to do with data, determines what you do with compute nodes and all of the rest of the things. We also then have something sort of separate, so this one works, and that we're just going to call a head node. And that really just looks after a whole bunch of management stuff. So that's pretty much really the high level stuff. Let's do this as well. And how it's configured. So these are the compute guys, and they've each got their CPU and RAM, and they're connected. Anyone know how they're connected? Pardon? Yeah, with networks. Anyone? Gigabit, 10 gigabit, InfiniBand? Anyone heard of those sort of things? Okay, so gigabit is the off-the-shelf, just normal network stuff. And that you can get away with very small clusters because the communication isn't too problematic. So they connected, how are we going to draw this? Let's just draw a network switch somehow. And they're all connected via the network to each other. The green one as well is connected. Okay. So those are pretty much the basic components. You've got network and various reasons why you choose various different types of networks. You've got your compute nodes, and you've got a head node to do the management and a data cluster. And that is the basic structure of high performance computing. All that really happens is that this then just expands to thousands, and this becomes a separate sort of entity. So this brings me to the first sort of topic, the difference between high performance computing and grid computing. Can anyone guess what that difference is? Or give a definition for each of them. Anyone?
Top connection. Network.
Almost, yeah?
Yeah.
network is a big part to play. So there's another. Okay. Can anyone else suggest anything?
Anything to do with how well it balances load?
It goes more towards what the load is. Anyone remember SETI? The screensaver? That is actually a very good example of grid computing. And why is that? Because again, we put it on your machine at home. It doesn't need to communicate with anything else. So in a grid, in high performance computing, every node has to talk to every other node and to the head node to solve a single problem, which means they need to access all of the data. You can't really do that by distributing computers around the world, because that communication overhead in a, sending a gig of data there to Tokyo and waiting, it'll just not happen. In grid computing you can. So the difference is grid computing has a work payload that is not dependent on any of the others' work payload. So you can literally package up its payload, tell it to do its thing, and it'll get back that information again. Or the head node would get that back. So grid computing can be distributed. A normal cluster can do grid computing and high performance computing, but a grid infrastructure cannot do high performance computing purely because of the network overhead. Does that make sense? I hear a lot of yeses. Any questions? No questions? Very quiet. Okay, cool. So that's the difference between high performance computing and grid computing. When your network scales to thousands of nodes and they all have to communicate, your standard Ethernet networks aren't going to actually make sense. You just cannot handle that workload. And that's when you get to the fancier networks like InfiniBand. So it's just extremely fast and expensive networking equipment. Okay. So that brings us on to the next topic, which is the data cluster itself. Your data infrastructure becomes extremely important because everything is always accessing it, and how you do that. So what typically happens is this is divided into a number of machines itself. So you can call it data 1, data 2, data 3. And the reason you do that is for redundancy, so that any one thing can go down and your data integrity is always maintained. So there's various ways to do that, and all of these guys still need to be able to understand where to get that data. Okay, so the typical Linux way of doing things is NFS, or network file system. It's a network file share, where everyone knows where to get that information. So this guy needs to know the same information that guy knows and that guy knows. And you do that all through the data cluster. So that's shared, it's like a shared folder in a Windows environment. The problem is when you get 1,000 nodes, or 1,000 computers, or 10,000 if you've really got a big cluster, all trying to access that information at the same time. NFS will just not be able to do that. It will just fall over. I mean, it started falling over when I just had 100 nodes, so it really just collapses. And this is where you get the high-performance computing things called parallel file systems. Has anyone heard of any parallel file systems? I'm not asking a bit much. So Intel's got its proprietary one called Lustre. Let me actually write that down. Parallel file systems. So Lustre. And it's sort of an industry standard. And it then distributes the data across multiple computers. Also, so that if two guys are asking for information, two machines can actually serve it. So it becomes extremely fast. You don't have to have one as redundant only. They're all serving the information. So that's pretty much the idea of the parallel file system. There are open source ones as well. So Red Hat does Gluster. There are others as well, but the documentation is not always as nice, and I've hit my head against them a few times. So BGFS. There's another one that I can remember offhand. Oops. Called Ceph. I think that's how you spell it.
What about IBM? Do they have something?
They've got their proprietary one, and I forget its name.
There's a Netezza and a Watson. I don't know which
Okay.
side of the fence those two.
So Watson isn't actually high performance computing in this. It's a computing system, but it's not clustered environment. It's something entirely different. Their file system, they do have a proprietary one as well. And the reason I don't know its name is because it's proprietary and I don't have money to buy all of the different tech. So those are, they pretty much all do the same thing. Just paid for free. That's relatively easy. Yeah.
Is that fundamentally different to storing an entire copy of your entire data set on each node? Or are there some big differences between those?
So if you want to think about these as RAID over nodes, and you can set up RAID in different methods. You can set up RAID 0, which really just has the data everywhere, not replicated. And then you can have it replicated and striped. You can set it up in any number of ways, depending on how many you've got. So yeah, you're literally replicating and spreading it out.
So is there always a network connection between the actual worker node and the data?
So that's quite important. What you really want is you want a separate network interface for the data sharing between these guys, so that when you serve that, it's not interfering with this. So you actually need a very fast interconnect. You can try and put it on the same network, but it's nice to have it as a separate sort of network infrastructure. So that when these guys are asking for information, it's a different channel. Yeah. So everyone familiar with RAID? There's one. Okay. Next question is, how does Hadoop fit into all of this? Everyone heard of Hadoop? That's quite a big buzzword. Does anyone actually know what Hadoop is or does? There's a half a mumble there. Very good. Distributed file system. Yeah. You want to elaborate? How would that fit into this configuration?
The data not stored on the same node as well.
So it's about the data and where the data is. So the whole concept with Hadoop was sometimes asking for data when the data amount or the data set is so large or it becomes prohibitive, your performance becomes very, very bad. So what do you actually do with this configuration? And what they do in Hadoop is they take all of this and they move it onto the nodes. So I'm not going to call them data 1, let's call them So what that means, and the marketing speak, is you don't need to move the data to the compute, you're moving the compute to the data. So the data that they need to work on is actually on the nodes themselves. It's good when you've got big data sets, and really big data sets, but can anyone guess why it's not good in other circumstances?
Duplicating a lot.
It's duplicating a lot of data, and it has to. And if you've got 1,000 nodes, is it 1,000 duplications, or does it need to figure out where to put things and which workloads need to go where? And figuring that out actually has a compute overhead, which means you're taking away. So in compute-intensive environments, that's just not really going to work necessarily as well. So when you use Hadoop, always depends. Like a good engineering answer, it depends. The answer is always it depends. So that's the concept of Hadoop. Does everyone sort of understand that? Anyone have got questions around that?
I don't even know what they are. I just like, how does that even work practically? Like, let's say I'm
So
a customer.
we're looking at big picture, but
Yeah.
ask a
So like
scenario.
if I own dataset D4 and I'm gonna bring a Hadoop processing node onto my dataset, how does that even work?
So what Hadoop does is it takes all of this data and distributes it. So
Across each node.
across all. So this becomes an Hadoop cluster. So, and then you do the processing where it is, and it does very fancy things of MapReduce and all of those calculations and what you need to do.
So is it not just duplicating, it's also selecting the right data for what we're going to give that
You
particular
can't
node to go
just
process?
duplicate, because if you've got 1,000 nodes
Yeah.
and you've got 50 terabyte data sets, does it mean each node has to have 50 terabytes? It does very clever things, but it's not a silver bullet. So where it's good is when you've got big data set and you've got to operate on that data. But it's not necessarily good if you've got a compute-intensive environment. So the trade-off always has to be made is, in your traditional HPC cluster, is the network not sufficient? If not, do you do a Hadoop cluster? It also does other things like RDMA. Anyone know what RDMA is? Remote direct memory access. So this guy can actually ask that guy's RAM what's in his RAM, and so it accesses things directly. That's a network layer sort of application. So there was a hand. There was a hand.
In terms of data analysis, so Hadoop's only really suited to specific problems as well. It's not just the. It's like, so in some cases we'd use MDCS instead of Hadoop.
Yeah. so it depends on what the problem is and if it's suited for, or if the technology is suited for the problem. And you've got to look at that quite carefully. Cool. Any other questions around that? Cool. So we're gonna. Yeah?
Do you have a Hadoop setup somewhere? Or is it not something you've played with?
I've not really needed to play with it. Traditional high-performance computing does not work with Hadoop. It's only big data sets that you really need to do that. And big data sets, they're sort of separate from high-performance computing traditionally, although everything is high-performance computing. So it really just depends on that sort of stuff. So I'm going to kill the Hadoop cluster so we don't get confused. Exactly. You can do some very cool stuff with schedulers and things where you do a Hadoop cluster on the fly and actually provisions it and puts the data, and then when it's finished, it kills it. But yeah, you can get that far. Okay. Any other questions? Conceptual questions? We're all happy. Okay, so that's Hadoop. So this is sort of a boring topic. But I thought we need to sort of cover it anyway. It's how you actually set it all up in software and what is necessary. So industry standards is Linux-based operating systems. So you can choose whichever torture method is suitable to you. I like Ubuntu. Fedora's breaking things. They change things too frequently, and then things break and they don't conform to standards. So Ubuntu seems to be working quite well. I don't want to go into the architecture too much of the software itself, but when software is written, it needs to know how to distribute pieces of a problem around. And that's called, and the way the communication is done is called MPI. It's a standard. and you might see that in Matlab stuff. So it's part of the management layers. Actually, write it here.
What does MDCS stand
It stands for Message Passing Interface. And it's a standard. There's various implementations once again. But software use this to make sure that the nodes can communicate and how to distribute the problem. So everyone done maths, matrix algebra? Anyone not done matrix algebra? Okay. How do you invert a matrix typically? What method? Gaussian? Pardon? Matrix laboratory, right? Yes. So Gaussian elimination, typically, you go through that process. How do you do that across multiple computers? How do you distribute or pass pieces off and do Gaussian elimination in parallel? So that's what most of the software packages do. And many people have come up with solutions on how to parallelize it. But that's typically what almost all engineering packages do. They're solving a matrix equation and they're doing it in parallel. So they're taking that matrix, distributing it, and inverting it. So when you get to a certain point and you need information, it'll ask that guy, what are you busy with? What's your numbers? And that guy and they'll talk to each other as they work as a team. Okay. Any questions around that? Yes.
So Google's PageRank algorithm, my understanding is that it's predominantly one big matrix inversion that calculates the
Yes.
Is that, to your knowledge, is that done?
I don't know,
Similar technique,
but if it's if the data size is that big, they would have to use some sort of parallel methods to do that. I don't see any other way not to. I mean, yeah, they'd have to have the data sort of sitting here and pieces and invert it if that's what they do. Yeah. Cool. The other management side of things is it's all good and well if you own all of this yourself, right? Because you can use all the resources and you can do what you want because you know what you're doing. What happens when you've got 10 people all using a cluster? It becomes quite contentious. You might get people shouting at each other and screaming and kicking. So this is where we get schedulers and resource managers. What they do is anyone who wants to run anything on a cluster, you give it to the scheduler. It sees, so one guy might want two nodes, but that leaves one free. So the scheduler says there's a guy that only wants one node, and they put that problem onto that. So you can actually run multiple jobs all at the same time and optimize the resources. So the scheduler really just looks and sees what resources are available, and you can run job 1 and job 2. There are certain intricacies around that, because these nodes have usually got multiple cores. And if you only need one core, it leaves 3 free, right? So theoretically, you could use those 3 cores on another job. Would you do it? So there's a no there, and why not? Everyone knows not to. It's probably from my facial expression, but why not?
Sounds like it gets complicated.
It gets complicated. You can do it, but the scheduler doesn't see what is being used. It just sees what this is reporting as I've got available. It says nothing about the memory, and jobs can actually start using more memory. And if you've got 2 jobs, all wanting all your memory, it's going to crash. So I prefer not to run multiple jobs on a node. If only one core is being used, you leave the rest free, and you pass it on to another node, the other jobs. So it's called a job exclusive. You don't want to run more than one job on a node. Yeah, you can do fancy things with containers to try and prevent it from using more resources than is requested, but that becomes complicated as well. And they haven't quite got that right. So schedulers, there's an open source one, or all of them are pretty much based on one called PBS, which stands for Portable Batch System. Yeah.
Sorry, kind of just going back.
Yep.
If the whole thing is that you can't do jobs on different cores, why isn't a node only made up of one core?
You sometimes get parallelism. So MPI is one version of parallelism. Then you get OpenMP. And this is the SNP, it's symmetric network, you know, the parallelism within a computer environment itself. So threading, that's why I just write that down as threading. So when you build a cluster, you don't necessarily just want to have one core, because sometimes you can actually have advantages with this. And even if you've got 4 threads or processes, you choose one node, it's much better usually than trying to communicate with all those guys. Now I say usually because sometimes there's a memory bandwidth issue. So if you've only got 2 channels and they're all trying to access the memory, you actually get a performance degradation. And it becomes quite important to understand your problem, and sometimes you can't predict it, so you've literally got to measure different problems and characterize the hardware before you go forward. So this is where it starts becoming quite complicated. Like I said, it might look really simple, but there's a lot of different little things that can creep in. Yes?
What is the job of the head node?
The head node is where your scheduler sits. So, yeah. Scheduler. Next one is called Ganglia. It's just prints pretty graphs saying some tools are being used, and you can print temperature and a whole bunch of things. So it just monitors what's happening. So the head node is really just to tell everyone else what to do, like a good boss.
So does he require as many computational cores as it is?
No, it doesn't. So it can actually be a dumb thing, like a good boss. just a dumb sort of head node, doesn't do much, just tells everyone else what to do.
Doesn't do anything with
I know what you think.
Doesn't do heavy.
Just trying to think of a good joke.
Yeah, I knew that.
Is it possible?
Yes.
Is it possible to have the head node also as a working node?
You
Like
can.
how good boss here, yeah?
Yes, you can. But they get confused. And then they don't do either job well. So that's part of the problem. What we've done, and you can do a whole bunch of combinations, is you can combine a head node with a data cluster as well. Because if there's not too much CPU overhead in your data cluster, then you've got free CPU stuff to do some head node jobs. So it depends, you can do that. Ideally, you'd want it separate. Okay. Any other questions? Cool. All right. GPU clusters. Everyone here understands about GPU shaping.
You're lucky the process guys on here today.
Yeah. So yes, question.
Sorry for the ignorance, but why is it that GPUs can't really communicate that easily?
It's to do with this communication, the software. It's not that they can't. It's that the software paradigms have not caught up yet to allowing people to write applications. Because you must remember, GPU applications are actually very problem specific. Until there's a need to scale that, I'm not going to put in effort to do that. So it's only now getting to that point where people are saying we need to scale our problems, and GPUs are the best for it. How do we do that across nodes? So that's where this comes in. It takes MPI, you can see the MPI part there. The MPICH is a open source implementation, and this part looks at the GPU side of things. Okay.
It's not the architecture.
It's not the architecture. It's literally the network communication and how the software knows to communicate where.
So typically you wouldn't be doing something on a GPU at the same time you'd be doing something on a CPU. So why does each GPU belong to a node which contains CPUs? Could it be a separate node?
You can actually do CPU and GPU simulations. So there's a cross-couple simulation. ANSYS do this quite well with a discrete element modeling that uses the GPU only. Then they've got fluid. So there's fluid flow as well as rocks. I want to simulate all of this. So it's a cross-coupled. So the fluid flow uses all the CPUs and RAM, and the discrete element modeling uses all of the other stuff.
To each other.
And they do talk to each other. Yeah. So and how they talk to each other is through your data. Okay. Any other questions? Yes.
Maybe you'll talk about this data at a high level, but just the kinds of problems that you would solve on GPU clusters versus CPU clusters, and then also FPGA clusters.
Okay.
I don't know if maybe you can talk about it.
I wasn't going to go to FPGAs, but we can go into FPGAs. Let's first talk about CPU, GPU, and then we'll go to FPGAs. So CPUs are general processing. The architecture is to be able to do general stuff, all sort of stuff, which means they sacrifice optimizing certain things. But matrix inversion, all of those things. Now this might show my age. Does anyone remember a math coprocessor? You might.
I'm still done getting.
So does everyone remember a Pentium?
Yes.
Yes.
A 486?
Yes.
Yes.
A 386?
Yes.
I think I used one once.
You used one once, right. The early versions of a 386, the CPU couldn't do floating point operations well. And there was actually a separate slot in the motherboard called the math coprocessor. You plugged it in. Over time, they merged together because it was just natural. And a similar thing is happening with GPUs. You'll notice that Intel has got a GPU on chip. So they're starting to merge. That doesn't go to answer your question. So the question is, general problems, matrix inversions, those codes are all written really well for CPUs. GPUs are only good at specific problems. They're not general purpose sort of problems. And at certain applications like computational chemistry, and only certain parts of it are good on GPUs. So it depends on the code and if the code allows it, what they do. FPGAs. Does everyone know what FPGA is? There's a no there, not necessarily.
Well,
So,
I said not necessarily, but everyone knows what an FPGA is. Students, how many of
Good
you
catch,
know what
Danny,
an
good catch.
FPGA is?
I'm not angry about that.
So any of our graduate students know FPGAs?
does anyone know what it stands for?
I know. Field Programmable Data Array.
Yay! Okay. So what does it actually do?
Lots of logic.
It's good. Like the name says, it's a programmable thing. You can actually program an algorithm into it, and it's really good at that one algorithm. But programming it is not trivial, and changing it and asking it to do other things is also not that good. So it's very good for specific things. Bitcoin? You don't know what Bitcoin is, yes? So that algorithm that they're trying to optimize as much as possible, so they used to use FPGAs to put that algorithm on, and so everything else becomes terrible. And they've taken it a step further. Everyone know what ASICs are? What does it stand for?
Application-specific integrated circuits.
There we go. Application-specific integrated circuits. So they take FPGA a step further and they actually create a chip that does only that one algorithm. So you can almost take that as a line. ASICs, very good, one thing only. FPGA is very good, one thing only, but it can be programmed to do different things. So it's quite emissions. GPUs, much more general, but only in certain areas. CPUs, pretty much everything. But the efficiency sort of goes up and down as well. Does that answer your question?
Yeah, because I think one of the reasons that FPGAs were designed was so that the obsolescence rates of CPUs, but particularly GPUs, is really high. So 2 years, for example, a GPU, and it's heavily outdated, and then the FPGA was more reusable, and then sort of stay valuable for longer. I don't know if it's...
So what they use FPGAs for in chip design is simulating that it actually works. So they use FPGAs when you get a new Pentium or a new whatever it is. All the design is actually done on FPGAs, and every clock cycle they need to simulate every state, and they use FPGAs for those sort of things. Cool. Any other questions on there? Okay, so that's GPU clusters. Next concept is burst to the cloud. Anyone heard of the concept? Yes, there. The boss doesn't know anything. Anyone got questions around that before I start? Let's just delete the GPU cluster.
How many people do you have locally currently?
Sorry, say it again.
How many people locally are currently bursting at a time?
I wouldn't know that, but it depends on what the application is.
I don't mean just
So
you guys.
I'm going to talk about high performance computing, and different people have different concepts of what bursting to the cloud means. Okay. So if you've got a single, let's just take all of these guys away as well. Maybe I must start with an analogy. High performance computing is pretty much like a rugby team, right? You've got a whole bunch of people all trying to work together for a single goal. If you don't have them as a single goal, you've got a losing team. So it's a team. You can think of them as the nodes. When you burst to the cloud and you leave half the team on one field and the other half on the other field, how do you get them to communicate? How do you get them to work as a single unit? So my concept is never have your team on different fields, always have them in one field. So bursting to the cloud, let's try this one. If you've got a local cluster, and say you've got 128 cores, your problem is actually just too big for that. The concept is, let's draw a cloud. The concept is, there's unlimited resources in the cloud. Push to the cloud. But what do you push to the cloud? Just, you get that to communicate with that, and this is where my rugby field analogy comes in. Having your team split means that becomes a problem, and you're actually back to a grid environment. So when you want to burst to the cloud, the better option is take that whole problem and push the whole problem there. You can have, say, 1024 cores, a bigger, better rugby team playing and doing the problem there. But to burst and to try and get just enough cores here, logically, you can do it, but performance-wise, it's just going to die.
The communication just slow it down so much.
Yeah.
Why would you, would cost be the reason why you would split it up? Or is there...
Cost is one of the because I mean you're paying here, this is yours. But when it's too big, you need more. So performance-wise, it might actually just run faster if you just put everything there, and cheaper.
Yeah.
If you have a few cores here, that communication, it'll actually slow it all down. So it might turn out more expensive in the long run if you do something like that. Any other questions around that? So that's my philosophy at least. In HPC environments, you take the whole problem and you move it.
how easy is it to use the infrastructure you've built out below the nodes and then be able to replicate that into the cloud environment?
How easy?
Because you want to progress as seamlessly from a local instance to a cloud instance as possible.
So the better way to answer that is how much experience you have.
Okay.
And the best, you need to have built these things to understand how they fit together. Your Lustre file systems. And if you have a look at Azure, you'll see that there is a Lustre file system. It's even Gluster and BGFS. Unless you've played with a parallel file system, you have no idea what you're doing here. And you might connect things very weirdly. So it's more about having that knowledge and then replicating it there. Because it is, you can replicate the entire logic. And you want them physically close together, the same rack preferably, because of that communication. So you can do HPC in the cloud, but you've got to be careful on how you set that up. Yep.
So is the idea of versus the cloud that it's also an overflow facility that you've got on-demand processing and from time to time you want to see what your load.
I've got another sort of rule of thumb thing, and it all depends on your workflow. Engineers, us, we've got like a little workstation where we build problems and we test things. When the problem gets too big, we need to scale it up to something bigger. Let's call it a 128 core thing. And you find a problem, so you've got to iterate back, fix your problem, push again. And only finally, when you've got your model right, and it usually takes, so the fluid dynamics guys take about 6 months of this, and they've got approximately this as well, locally, to get the model right before they put to like thousands of cores. So they know the model is right, they iterate locally, and then once they know that's right, then they push to a cloud or HPC facility. And it should only be a once-off thing, cost-wise. If you're a heavy user of CPUs or compute, cloud actually never makes sense. And there's a nice sort of graph. We did this, Alaris. Anyone else know Alaris antennas? So we did this exercise for them because they got a local compute thing, and they needed to know the numbers. When will it be paid off compared to cloud and all those sort of things. So if you buy it, there's a once-off capex. Maintenance can be built into that, which is what we sort of do. Cloud is pay per use. So as you use, it accumulates. There's going to be a crossover point here. And when do you think that is?
What, in years? Or money?
No, in time.
2 months.
Almost. For them it was 16 weeks, I think. They are a very heavy user, so in other words, they keep their machine busy, but that cost, if they translated that into CPU hours in a cloud environment, would have been just prohibitively expensive. Now, they're not worried about that cost, and they're doing actual design exploration. They're just pushing things to the extent that they are now fighting and kicking, even though they've got a scheduler, and they're telling each other to get off the cluster so that they can use it. So it's a very interesting sort of study. Their cluster is a 36 core. The simulations aren't huge, but they've got many of them. Bursting to the cloud. I put MDCS there to try and compare how that fits into a traditional HPC environment. And anyone other than the MDCS person, can you guess how that fits in?
What's the question?
The difference between this and let's call it your management, because that's all this really is. It's a management layer compared to that. And more importantly, can they coexist?
It doesn't have the data cluster, as far as I know.
That's more of the hardware setup.
You can, so you can split the files locally on the machines. Depends how you set it up.
Good engineering answer, depends.
I think that the Matlab code you write has to know how to retrieve the data. So the standard approach is to just fix it. You can either put it all one place, you can distribute locally, but each worker has to know how to retrieve its data. I don't know how that fits into if you're going to use a more complex file system. I don't know how it would work, but
So
There are also different ways you can apply the parallelization. So you've got the par for loop, which is your traditional for loop that you can run, that will run on the different nodes. And then you get the single program multiple data, where it operates similar to the distributed file system. You actually distribute the data and have one algorithm working for all the different types of data. So you've got some flexibility.
So how it really fits in is actually in all of those scenarios. It's just that it doesn't play nicely if you've got other applications using other things. Matlab and this works nicely in its environment, but you do need them to talk to each other and work together. So in Linux, they actually do work nicely together. In a Windows environment, it's much more interactive, setting up those scheduling environments and resources, and it doesn't play nicely. But in a Linux environment, they actually do coexist. So the PBSs and all of these things actually do work with the Matlab environment. So you can, and many universities actually internationally. I spoke to the PBS guys specifically. They've given me their scripts and how they do it. So we can actually do that and put Matlab on a traditional cluster environment. Any other general questions? I think that was quite a lot of information.
Well, maybe you can explain like how what CrunchYard thing is versus Microsoft Azure.
Okay. Maybe a bit of history. So I worked at Pointing, which was an antenna company, and they had their software package called SuperNIC. And one day we sat down and said, how do we do this differently? How do we commercialize it differently? And Andre Farid said, well, let's put it on the internet on a pay-per-use basis. And that's where it really started. So try to figure out, took a year to figure out how to do this, and constructed a cluster with a web front end so people can just submit jobs and it just goes through and you can get things processed. We very quickly realized antennas are some of the smallest simulations you can actually get. Exploration geophysics are some of the biggest. So seismic, this was about 3 years ago. The big problems they were talking about, the input file, just the input file was a petabyte, and they needed 100,000 cores to solve that. So that's big. We weren't anywhere near that, with our small little cluster. Over time, so we offered that and we started putting more applications on. Over time we realized, and our clients actually said to us, the workflow doesn't actually totally fit that. And that workflow that I did previously, of your workstation, your local compute, and then cloud. So we've done the cloud. And now we're busy with things called crunch stations. So you can actually get 112 cores on a single box. With its own scheduler, so it's a mini cluster, so it's on your desktop. So you can work together locally, and then this can then push or talk to the queuing system of the cloud environment. So that's actually what CrunchYard's doing now. Where we're partnering with Microsoft is that we're still doing this, but we do that setup in the cloud and set up those architectures for people in the Azure cloud, and we partner with Microsoft to do that. Does that answer the question? Very general.
Yes. I think people will be very intrigued to hear how you set up MDCS on the Crunch Station?
So that's what we're busy with at the moment, is the prototyping. Just draw the workflow again. Workstation. Crunch Station. I'm going to call this Azure / CrunchYard. So what we're busy with, and busy with Kirsten and Daniel Talita, is guys have got their code and they're writing it. They might have licenses, a certain number of licenses that they can then push there, and they can test things locally. And you have your MDCS and GPUs and a whole bunch of things to do those local computes. And obviously you get testing and you can do that until you get a bigger environment, and then push the Matlab stuff there. And that's why I mentioned PBS talks nicely to Matlab or to MDCS, because it was part of my big concerns. How do you get the environments to talk to each other? So I haven't actually played with it, but I've got the code to do that. So that's pretty much what we're busy with, is putting a proof of concept together for this environment, so that people can go to extremes with their data when they need to.
So how would that work? Is that like you pretend that Azure is like an MDCS, or like how does it work with Matlab?
So instead of calling it MDCS, just call it a resource manager or queuing system, because that's all that MDCS really is. Resource. When your resource manager says there's no more resources, it talks to this resource manager. And this guy says, I've got stuff. And then it says, okay, here we go, please do this. So it's the resource managers that will be talking to each other, and you can obviously enable or disable that talking.
So does PBS replace MDCS when you get onto the cloud to go and scale it up there? Okay. Interesting. I wonder what that looks.
Not necessarily.
Okay.
It's going to depend on what the proof of concept shows. But it'll be nice, seeing as PBS does talk nicely with Matlab in a Linux environment. That would be a nice thing to do, because it's a standard.
Yes.
And then you can actually do other things, like other software programs, like Polaris. They've got their Matlab stuff. And they have little code to interact with FICO.
Okay. Yes.
And FICO works very nicely because it's actually owned by the same company now. PBS is owned by Altair. So they talk nicely together. So to get at that homogeneous environment is perfect. Yes.
There's a company called Tequila. Tequila.
The name half rings a bell.
Yeah.
Saturday nights.
Training in Belgium, right?
No, I came across it somewhere else. It's overseas somewhere. But effectively, what they do, they offer a service where, and I was surprised by Matlab, one of the things that they said they can use, where you will have, they'll say, you've got an application, say it's a Matlab application, and they can scale that to the cloud straight away. So apparently they've got something, I don't know if it's software or if they have hundreds of people that will be coded overnight. But apparently overnight you'll have something that can run with massively parallel environments. As far as I understand, it does not use MDCS at all.
It's MDCS is just really a resource manager.
And a source of revenue.
And a source of revenue, yes. The way that they must probably do it is look at path wars to instantly get massive scaling, because that's easy. But certain applications cannot be parallelized. They literally cannot, and bioinformatics is one of them. So they rather have a single fat node with a terabyte of RAM to fit all the data in than to try. This, by the way, is called a distributed memory paradigm, because the memory is distributed, so your RAM is distributed. You can take a problem and distribute it. Shared memory is where they obviously share, where you've got a big thing and they all share the same RAM. So I'd be very surprised if we can take any problem, because
I'm sure that was a market scheme. I was
sure.
interested in, and maybe it's the workflow there between the crunch station and then moving on to something that's perhaps Azure.
Yes.
Where MDCS fits into that. Because even your Power, for example, I'm incredibly clued up on this, but in theory you still require MDCS
Yeah.
on
So-
the licensing side at least to run that.
You'd still keep it there, but the resource manager would be PBS. You wouldn't rely on necessarily MDCS to do it. You might, because we can actually partition that off as a separate cluster. But then, how do other applications that you might want to interact with work?
And also the licensing issue. Obviously, people buy a certain number of MDCS loads. So what does that mean? Are they eligible to go and pay a bit more to?
So that licensing models is a whole talk on its own.
Yeah.
Because it's a minefield. It's actually the biggest problem people face. It's not the technical stuff. The biggest problem is licensing. How do you talk to licensing? What are the various schemes? Because some of them go from you're only allowed to use a license within a 5 kilometer radius of your work. In a cloud world, it's very weird. To you can use unlimited nodes for a certain license for a certain. So you pay for a month, and this is the Star CCM guys. They say unlimited nodes for your power license for a month. You buy that and make sure you use that. So the licensing is quite a minefield. So the better approach is to have a licensing manager sitting in Azure somewhere, because then locally you can connect to your license manager, and when you're in Azure you can connect to the license manager. You don't have to worry too much about trying to connect from there through a firewall here somewhere. So this setup is actually better. Have your license manager sit in the cloud.
Right.
Yes.
In terms of data, if you worked on your workstation, now you've upgraded to the Crunch station, how would you actually, would Azure then access the data that you have on the local machine? You have to transfer it, upload it into the web? How would you actually manage that?
The better solution is actually to transfer it. And I know it's an issue when you get large data sets.
Yeah.
But you do one transfer up, you put it there.
Yeah, so it won't be a good idea for petabyte data.
No, you can ship hard drives.
Okay.
And some simulation companies actually say they're in the business of shipping hard drives. The data analysis is just by the way. Shipping hard drives is still a viable option, but with fiber coming, and I might not have mentioned this, but Azure is building a facility in Johannesburg. So you're going to get much faster access to stuff. So
Okay, so people can drop off their database.
petabyte, I'd still recommend you go. But petabyte, I don't know if you know how many hard drives that is, how heavy that actually is. It's, you have to have your own facility pretty much dedicated for something like that. Yes.
Who's currently using CrunchStation?
Who's currently? So this the bigger one we've got is 112 cores. That's ESCOM's Specialization Center for Combustion Engineering. It's a research center at BITS. And when they model their boilers, so they've got to model how they inject coal with air and swirl it. And they've got to swirl it in various ways so that the flame is right to get the right burn rate and energy out of that. That's complex, extremely complex, because that's fluid flow, particle flow, thermal. It's all of these multi-physics things. So they are one of the biggest users of this. And obviously Alaris have got a smaller version of this locally as well. So it's quite a new thing. But those are most of the we've got quite a lot of interest. You can do actually more with this. Another client had a weird request. They've got an application that uses Microsoft's SQL database, but the performance was not quite good. To buy more licenses, to go multi-core is prohibitively expensive. So they came to us and said, is there another solution? So we came up with a hardware solution instead, which uses many SSDs in an array and parallel file configuration. So you get near RAM speed from your hard drive, which improves your performance without going multi-core. So that was a sort of a weird combination of things, but it worked quite well. So parallelism and redundancy and performance. Yeah. Any other questions? Okay. Well, thank you very much for listening, and thanks for interacting.
Thank you.